this is a little tutorial put together to cover open and closed loop op-amp circuits. Now if you're not interested in op-amps, I'd suggest you move along, but if you are, stay tuned and we'll cover the basics. So as I've previously discussed in some other sessions, semiconductors often have very dubious parameters. They are mass-produced so quickly and so cheaply that they're quite often way off tolerance, and they generally get around this by specifying very large minimum, maximum and typical values, big differences between them. So when we're designing an op-amp circuit, one of the ways we can overcome this is to actually design our op-amp circuit to have a much higher gain than desired, and then what we can do is reduce it down afterwards using something like feedback. Now that is much more desirable than going through the process of designing a circuit, constructing it, and then finding your gain is way under what you expected. So that's something to consider. Okay, in today's tutorial we're going to be investigating the types and effects of feedback on an amplifier's performance. So we're going to consider the different types of feedback that might be used and also the effects that they have on the amplifier's performance. The types that we'll be looking at are open, we'll be looking at closed, and we'll also be looking at positive and negative feedback. Now with open and closed, they're usually referred to as an open loop circuit and a closed loop circuit. Of course, using feedback has different effects on circuits, and one of the effects it has is the overall gain, so the maximum amplification of the operational amplifier, the bandwidth of the circuit, and when we're talking about bandwidth, we're talking about its frequency response. How well does it amplify small frequencies, low frequency? How well does it amplify the larger frequencies? And what we're looking for is its amplification here, and anything less than its desired amplification is a reduction in gain, and we can actually tailor the circuit to give us the desired gain values and the desired bandwidth. Distortion. Now distortion is referring to the kind of input wave regarding the output wave. How true is it to the original? Is it stretched out? Is it out of phase? Is it distorted? And then sometimes we might also introduce noise onto this signal. So this is actually interference, glitching, spikes on this output signal. So that would be noise. Now stability is another thing we'll consider eventually. If we have a look down here, stability is essentially, if our input signal is here and our output signal wants to be bigger but also there, does it remain equal? Is 0 point here? Does this output signal actually shift, or do we actually get some sort of inconsistency here in perhaps an oscillation? So maybe when our input signal is stable at 0 volts, we might actually have some wobbling on the output or oscillation going on. Now this is often undesired, but we can also put this to good use if we actually design an oscillator circuit, so something where we actually want the output to vary. And the other two terms we're going to be looking at are input and output impedance. So if we draw a little amplifier here, well, we don't just have a straight circuit into the chip and out. The input and output have a very large resistance inside, and that's in ohms, and resistance in ohms. And usually the output, for example on the 741 chip that we'll be looking at today, I think it's about 50 ohms. I might be wrong, might have to double check that one. And the input resistance is usually very large, kind of 2 mega ohms. And that really means that we can make use of the full signal available here, so there's very little voltage drop on the input. So as mentioned, I'm going to do a few. The calculations we'll be doing are actually based on the 741 op-amp. It's a very common op-amp IC that you can get hold of. As I mentioned, the term open loop is referred to an op-amp circuit that does not use feedback in its operation. as operational amplifiers have extremely high gains, and ideally in the ideal world they would have an infinitely high gain, but in reality they don't have an infinitely high gain, but they've got many thousands of times gain. That means that any small input voltage will easily cause the output to reach its maximum voltage, and when the output reaches its maximum voltage we call that saturated. Now usually its maximum output voltage is going to be VCC, and that is whatever you've got your op amp connected to. As a power supply it could be 10 volts, 12 volts, 6 volts, 24 volts if you desire. So one thing we're going to have trouble with in an open loop circuit is actually using the amp getting a useful voltage out if we're trying to get a desired gain. Now to actually do the calculation we're going to need to grab some numbers off the data sheet. One of the numbers we're going to need is the kind of open loop gain. Now it's not always clearly defined as open loop gain, but on this particular data sheet it is specified as large signal voltage gain. What it does on the other end is it tells us that for every 1 millivolt going in we're going to get 200 volts out. So we can actually work out the gain, or A, with 200 over 1 millivolt, and that will actually give us a open loop gain of equivalent 200,000. So the A open loop equals 200,000. So that's quite high. That's not exactly the output. We'll figure that out in a little bit, but we'll stick with this number for A for open loop gain. The next thing we'll need to know is the actual input resistance inside the amp. So as I mentioned in the previous picture, that resistance is inside the chip, and in this particular one it is 2 megaohm. So some of the newer chips anyway have a much higher resistance than that, but I'm going to stick with this one, and that is our RI for resistance at input. Here is an example. These are the things that we've already found out. The gain is 200,000. The resistance of the input is 2 megaohm. I did look it up on the data sheet actually. I think I said 50 ohms, but it's actually 75 ohms is the output resistance. Also, we're going to stipulate that we're going to put V in at 0.5 volts. So this is pull in from the power supply. We're specifying this. Now 2 megaohm for RI do actually have a 10k resistor on the input here, but really 10k added to million is not a tremendous amount more. So yes, we will have a slightly reduced voltage than 0.5 volts on the input, but just for ball of park figure we're going to stick with 5 volts. You could work it out, but it's only fractionally smaller than 0.5 volts, so it just makes it a little easier to stick there. We can actually calculate the voltage out now. We take voltage out is equal to the open loop gain, or A, times the V in. If the V in is 0.5 volts, the V out is going to be 100,000 volts. Very unlikely, as you can see, too much voltage. In reality, it's going to max out, and it's going to max out to whatever your VCC is. So that's limited. So yeah, as you can see, a very small 0.5 volts in, we're aiming at 100,000 volts out. It's not really going to happen, okay? But actually, if you've got a really tiny voltage here, you might be able to get this down to VCC. The other thing to consider is our offset voltage, because the offset is going to be, it could be a tiny amount out here, but over here it's just going to be hundreds of volts out. So we'd really have to have a huge supply voltage across this chip here, way more than the chip could actually handle. But that's why we're going to deploy some form of feedback. So here we have some small signal output here. So some of the output signal is fed back through this resistor, feedback resistor, or RF, and it's actually pushed back into the input. Now to note, for this to work it must be into the inverting input. We've still got R here at 10k, and RF I've just chosen a ballpark figure of 22k. Okay. Here the closed loop gain is actually equal to this formula, which is the voltage out is equal to the feedback resistor divided by the input resistor times the voltage in. And here we'll stick with the same numbers as we did before. We've got the V in set to 0.5 volts. We've got the RF is 22,000 ohms, and the the R resistor, the input resistor, is 10,000 ohms. So that equals out to be 22,000 divided by 10,000 times 0.5 volts equals. So that's it really for open loop and closed loop examples. Generally, when we're deploying an op amp in most circuits, we'll use some sort of feedback. I have a very crude example here of the op amp 741 running in an open loop mode. So there's no feedback being taken from the output on pin 7, which is going out to this multimeter. Now it's currently connected up to two sets of battery packs that give me about plus 6 volts and minus 6 volts. So this is running off a dual power supply. I'm running the voltage in down this green wire to the inverting pin, I believe. And what you'll actually see is I already have 5 volts on my output, so the output is already fully saturated, and I'm actually running at 0 volts on the input. There's quite a bit of noise on there, and in this mode the output will actually vary to that noise as well. It's that sensitive. So as we increase this up, and we've increased it now by about 20 millivolts, keep going, you'll see that output starts to change, and around about there it switches. Oh, I've nearly got it off there. Okay, so it's about 0.4 volts, but look how much the input is varying. I'm varying it less than absolute millivolts here, and you can see the output is jumping up and down, and that's actually this noise on the input. I don't know where the noise is coming from. It might be coming from the power supply, it could be coming down the leads, it could be coming from a light, it could be anywhere, but that little spike in the middle there is actually superimposed noise onto the input. And if I was to connect the scope up there, I could see the output as well. I'm not entirely sure about this interference here. Something is causing me some trouble, but this tiny little spike on the blue line is literally maybe 20 millivolts at the most, and the output is spiking in rhythm to that, and it's pulsing up and down about one and a bit volts there maybe. You can see there it's flying around all over the place. Now if I increase the input in blue up a few more millivolts, oh there we go, you'll see the thing completely switches on. Wrong control, there we go. So you can see the input does switch on and off. It does go between positive and negative, and you can, very annoying, this thing shuts down, you can just about get it in the middle if you're very careful. But obviously, as we said, we've got a gain of such a large amount. It's so sensitive that other than using it for a comparator, it's not going to be much good. So now I can introduce the 22 kilo ohm resistor, and that's going to go between the input and the output. And you can see now that the voltage has dropped, and as I bring the input voltage down it goes up, and as I bring it up, as it's an inverting amp, it goes down. Now theoretically, if I pull in what we calculated, and let me double check my notes, if we put 0.5 volts in, we should be getting about 2.7 minus 2.7 volts out. and just change the scaling here. We'll change that to 0.5 of a volt. Great. We'll go from 0. Now, bear in mind that this doesn't go to 0 when I set it to 0. That's why we have an offset pin on here, and we can actually use a variable resistor to tune the offset so that when the input's at 0, the output is exactly at 0. So I've got to find that point close enough. Where is it? Okay, so that's close to 0. And then we need to bring up this input up about 1, 2, 3 blocks. So 1, 2, and about 3. And you can see 0.5 volts in, and I'm getting minus 2.63 volts out, which is very close to what we calculated. So that's the benefit of using the feedback. And of course, if I disconnect the feedback, it's just going to shoot to its maximum point there, isn't it?